Now that we're all in pre-calculus, it's time to raise the bar. To learn how to calculate the area under the curve of a graph, you have to know some basics first. Sigma notation from afar may look intimidating, but really it's as easy as addition, because that's all it is. Sigma notation is used to calculate a long list of sums. So if you're adding a long list of numbers together, sigma notation will save you time and make your life a whole lot easier. The Greek letter sigma indicates the sum. The letter under the sigma is the index, and it corresponds to the indices both on top and on the bottom of the sigma. You will take each indice and input it into the argumentation of summation. Great! Now that we've learned about sigma notation, we can apply it to help us find the area under the curve. Let's use an example to help illustrate the steps needed to take to find the area under the curve. You are driving your fancy new race car and all you want to do is go fast. You accelerate for 2 minutes until you hit your max speed of 200 miles per hour. For some odd reason, you want to know the distance you covered in those 2 minutes. You pull over and park safely on the side of the road and pull out your handy-dandy math pack. On a piece of paper, you graph your acceleration, knowing that you started around 50 miles per hour and you accelerated at a constant speed of 75 miles per minute. The next step is breaking up the area under the curve into different segments, or rectangles. For our purpose, we're going to break up the area into 4 parts, which we'll refer to using subscripts. We are first going to find the area using left endpoint rectangles, which means we're going to find the area of rectangles whose left endpoint is touching the graph. The parent sigma notation we will use is this. We already found the base of the rectangles, 0.5, which we can input in this part right here. Now all we have to do is find the height of the rectangles. We do this by entering our x subscripts into our original equation of 75x plus 50. But first, we have to find a way to set our subscripts equal with their values. We do this by multiplying our subscripts by 0.5. So our new equation looks something like this. Take this whole piece and input it here in our general sigma notation, and now we're ready to go. Now all we have to do is input this in our sum programs on our calculators, and make sure the beginning indice that we put is 0 and our end indice is 3. You should have gotten 212.5. This estimation is called a lower bound because our estimation is smaller than the actual area because of all the unaccounted space between the rectangles and the curve. Now we're going to find the area under the same curve as before, using right endpoint rectangles instead. Don't worry, the process is nowhere near as long as it was before. In fact, we only changed 2 things, and those are the begin and end indices. Instead of starting at subscript 0, we're going to start at 1, and instead of ending on subscript 3, we're going to end on 4. This is because the rectangles have changed. The area we're estimating is over the graph, because of the right endpoint rectangles, an estimation that we call upper bound. After putting these different indices in your program, your answer should now be 287.5. A good way to make your estimation as accurate as possible is to take the difference between the 2 estimations and split the difference, making our final estimation 250. Let's check our estimation against one last way to find the area under the curve. Trapezoids. If you observed, the rectangles we used are in fact trapezoids, and if we solve for the individual area of each trapezoid, then add them all together, we'll have a pretty accurate estimation for the area under the curve. Our grand total is 250. But we're not done yet. If you recall, our original problem states that we were traveling 200 miles per hour, not minutes, which is how we set up our independent variable. It's a problem easily fixed. Just divide 250 miles by 60 and our final answer is about 4.167 miles traveled in those 2 minutes of acceleration. Thanks for watching, and I hope you learned something interesting that you can impress your math teacher with.